Hi, friends. I miss you so much. And I don't know how long this is going to work out with just like having me in the corner right now. I might just do my screen because and who wants to see this? But I miss you and I miss your faces. And not that you miss my face, but I'm just saying sometimes it is nice to just have a face with everything that's going on. Basically, what I have here is the blank PDF that I attached to the lesson. You can print this if you want and just write on top of it. I'm going to do my best to do this here. I don't have a functioning stylus right now. This is one that my dad loaned me, and it doesn't work so great with my computer. So we're going to see how this goes. So, introduction to first order linear systems. Now, everything we've done with differential equations has been with single differential equations. Chapter 4 is all about systems of differential equations. So, I'm just going to go to the next slide right here. So, basically, what we're going to have is we're going to have dx dt and dy dt. So, we've got basically a system of two differential equations right here. This f1, f2, f3, f4 can be coefficients, but they may also be functions of our independent variable, where in this case, because we have x and y, they're both functions of the independent variable t. So in matrix form, and this is why we did so much work with matrices in chapter 3, just in the middle of chapter 3, is it makes it a whole lot easier to solve systems. So basically, in our matrix form here, we would have x prime, y prime, again, just coming from up here where we have dx dt, dy dt. We have our coefficient matrix, and again, those could also be functions of t, or they may just be nice numbers, which would be great as well. Here, x and y, this is going to be our vector value function. Oh goodness, this is going to look great. Vector valued function. Yeah. I have a copy of this from last year with much better writing on it from the Smartboard. I will hopefully get a little bit better at writing on here in time. Just give me time. Basically, though, when we do take notes, since these are vectors, we remember use the notation of a vector like this. The book will use bold letters. That obviously doesn't work so great for us. So I'm just going to get rid of that. So we use our vector notation here with this little partial arrow on top. So you'll see that in my handwritten notes as well. Now, if we have a system of 3, then it obviously looks like this, which is where matrices come a lot more in handy here. So again, this is our vector function right here, x, y, z. All right, so that's kind of the idea of matrix form right here. We'll go to the next slide, which is talking about the limit of our matrix system right here. So let's say we have the matrix A of t. So this is just kind of like this could be our coefficient matrix, where they could just be straight up coefficients or functions of t, like you'll see with our example down here. Now, instead of me writing it all in because it's awful, I do have the previous notes I'm just going to pull up here. So if we want to evaluate the limit of our A of t, then what we do is we essentially just take the limit of each individual element as t approaches x, or whatever it is that we're evaluating here. So for each element, we independently evaluate the limit. So what that looks like for b of t right here is that we would want to evaluate the limit for b of t on part A here as t goes to 2. So I know this is already kind of written out for you here. You can pause and you can try this yourself because this is in our notes right here. But if we want to evaluate as t goes to 2, well, then we would evaluate 2 in each of our elements here. So obviously we get 0 there, e squared right here. So basically what's happening here is the limit is this new matrix that represents what each element's limit is as t goes to 2. Okay. Now, as t goes to 0, we see that this falls apart. The first element here, just 0, that's fine. But here we would get 0 to the negative 1, which is 1 over 0. Because it does not exist for this single element, that means the limit does not exist as t goes to 0 for all of b of t. Okay, so we would just state that the limit does not exist for that specific example. All right, now derivatives function in the same way. If we have a of t, then we evaluate the derivative at each element in that matrix, okay? So that's easy enough. Finding limits, finding derivatives, you just evaluate for each individual element. So what we're going to do is I'm going to head back to my blank notes over here. All right. So as with limits and derivatives, antiderivatives of matrix functions can be found by anti-differentiating each component. Okay, so now if I have a prime of t and I know that it looks like this matrix right here, let's say we want to find what a of t is if we know that a of 0 is equal to this matrix right here. So what we're going to do is we're going to go ahead and anti-differentiate each component here to find what a of t is. And we're going to add c, but what we're going to do is we're going to add a matrix C at the end. So we're going to have C1 through C4, and that will come a little independent of our matrix A of t. Okay, we're going to give this a try here. A of t equals, so anti-differentiating here, t squared. Here we would get t. We get sine of t. And here we would get t to the third. So what we're going to do is we're just going to add c on at the end of that. Okay, we can do some matrix operations here with this if we kind of then take into account that basically what we have for a of 0, evaluated at 0, would be this same matrix. Plus each of those respective c values. And we know that that's equal to this matrix that we were given up here. So in a way, it's our initial value problem. So I'm going to give you a second here. This is just solving by plugging 0 in now for t. So we could do this individually, and really you could. I mean, you could just say t squared plus c sub 1, t plus c sub 2, and just solve them individually. That is fine. If you do it in the matrix format here, then, essentially you're just doing your matrix operations. So if I plug in 0 actually in place of t in each of these, we are going to get the 0 matrix, which makes this really easy. Because if that's the 0 matrix, then that just means that we actually have C1, C2, C3, and C4 right here. Okay. Now, if those are all of our C values, then what we do is we go ahead and we go back up to A of t and we plug those in A of t to get our full matrix for A. So I'm going to go back to my written notes here. It'll be written out a little more nicely. And again, these are the ones that I'm going to post. Okay. So if we have C1, C2, C3, C4 right there, again, just plugging them in with their corresponding elements right there. Okay, so that's really it for antiderivatives. Now, derivatives, antiderivatives, limits, all pretty straightforward. You're just doing operations that you're familiar with. You're just doing them with each element in the matrix. The reason why we would want to be able to solve a system is really going back to our tank problem. So we did tank problems when we were first discussing differential equations, and it was limited to just a singular tank. So what we're going to do, and I'm going to go ahead and quit this video here and just do this in a separate problem or a separate video. I'll go through and I'll show you where our systems of differential equations can be helpful when it comes to the two-tank problem. You can watch that one individually. There are a couple problems in the homework. The rest are just evaluating limits, derivatives, antiderivatives. So I'm going to stop this video here, do a separate video with the two-tank problem.